All right, we're going to talk about linearizing and solving for a variable of interest. I know there's another linearizing video that is just the basics of how to linearize, but the goal of linearizing is not only to simplify a relationship, but also possibly to use that simplified relationship to uncover a variable of interest. And by that, I mean, if you have a data set that describes a falling object, such as this one does, then the reason an object falls is because of gravity. And you might imagine that if you conducted this experiment on Earth, you get one set of data. If you conduct it on the moon, you get a different set of data. And that set of data somehow depends on gravity. And so the goal is to use this data to actually extract the value of gravity, to actually determine what G is just from this data set through the process of linearizing. So the steps to the whole process are these. First, we got to linearize the graph. Second, we need to get a linear equation from that graph. Third, this is the jump, match that equation with a known physics equation. There's got to be some physics equation which describes this phenomena that this data set is revealing. And so we want to determine that known physics equation, and then finally use these two equations in conjunction with each other to solve for a variable of interest, which in our case, for this example, will be gravity. So starting with the data set itself, we've got a data set of an object being dropped at time 0, at position 0, and it's going to fall. You know, you're like standing on a cliff and you have a rock and you just let it go and down it plummets. And so after each second, it has reached a position down below you of these values. So clearly, this is not a linear set of data. And so the first step in linearizing is just recognizing, based on your physics experience, what is the most likely relationship that these two axes share with each other. And from our insight, from our intuition and experience, we've got very few to choose from. In physics, there are really only a few that we're going to be likely to see. In all of math, there are hundreds, possibly thousands of relationships, but physics is a little bit narrower than all of the possible ranges because physics abides by a relatively small number of laws, and so those laws are summarized in a few equations. So clearly, this is not a linear set of data, so it's not that. Quadratic, we have hope there. Inverse, as one increases, the other decreases, not happening. And root, as one increases, the other also increases, but less quickly. So this does not appear to be a root graph. So it looks like quadratic is what this is. So I'm going to start by just saying, oh, this looks like a quadratic. So as far as math is concerned, the form of this relationship would be y equals ax squared. Now we got to dig in a little bit to first linearize it and then extract the linear equation. So this math equation essentially tells you what you should do to linearize your data. So if it's y equals ax squared, that tells me that I should probably square my x-axis. So what I'm going to do is I'm going to try to do y, which would be position, versus time squared. So I want to square that data. So I want to take my time data and square it. Time squared, that's going to be 0, 1, 4, 9, 16, 25, 36, 49, 64. And now I'm going to graph position versus t squared. And oh, look, there it is, position versus t squared. We got position here, we got time squared here, and check that out. It is really, really linear. I feel great about this. The fact that it appears linear convinces me that I made the right choice initially. Was it quadratic? Yes, because I linearized it the way I would linearize a quadratic, and now it's straight. So that's confirmation. So I'm going to go back to this. My math equation was y equals some constant times x squared. My graphical equation, like the one I actually have right here in front of me, is position equals, well, I have a value. I have an m value. It's of the form y equals mx plus b. So I got my m, my slope, 5.1, I'm rounding, times the time squared. And I also appear to have a b value, a y-intercept, minus 1.4. I'm just going to call it 1.4. So as a brief aside, you might think, is this b value, is this y-intercept of interest to us? And the short version is no. The slightly longer version is why no? Well, this value right here, the slope, is our rate of change. As one thing changes, the other changes at a certain rate. And so that's what gives us the overall shape of this graph. Is it straight? Is it curved? And this is useful. This is of interest. The y-intercept is really just an offset. Is this graph here? Is it down here? Is it up here? It would have the same relationship, the same rate of change, regardless of the y-intercept. And so I don't really care about the y-intercept. It's not useful to this analysis. Y-intercept, not useful. And so that's why we are able to ignore it, because it really doesn't tell us anything that we need to know. So what we're left with then is this equation, position equals 5.1 times time squared. And now here comes the tricky part. Let's see, looking back up. Linearized graph, check. Get linear equation, check. Match that with a known physics equation. This is where the jump from math to physics occurs. So we know that a dropped object is changing its position in some way due to the time it has traveled. And there is a very useful, very familiar physics equation. That is delta x, or d, equals VOT plus 1/2 AT squared. Now, at first glance, position equals 5.1 t squared is not exactly mapping to this equation right here. But if we consider that this object has been dropped from rest, then that makes this original velocity go to 0. So what that gives us is d equals 1/2 AT squared. Now, these two equations are basically the same equation. They are saying exactly the same thing. Our experimental data is revealed or described by this equation. The theory is that it should behave according to this equation. And they are the same equation, where position equals d, the displacement, of course, t squared equals t squared. So we can set these two equations equal to each other. And thus, as you will shortly see, we're going to extract a value of what the acceleration is. We didn't know what the value of acceleration is. We kind of knew that it was happening, but now we're actually going to get a quantitative value for it. So if we set these two equations equal to each other, we can say that 5.1 t squared equals 1/2 AT squared. T squareds cancel. So I got 1/2 of the acceleration equals 5.1. So that tells me that my acceleration equals 10.2 meters per second squared. And since this was a falling object, that acceleration is actually the acceleration due to gravity. And so we've pulled it off. Through the skill of linearizing, we've allowed ourselves to, we linearize the graph, we get the linear equation, we match that with a known physics equation. Essentially, this is your experimental equation, and this is your theoretical equation. And so in any experiment, it should match with some theory. That's what we've done. And then the last step is algebra. We match those. By matching those equations, we can then solve for the thing we're interested in. And This is essentially the same process that you're going to use for determining your value of G in the pendulum lab as well. If you have more questions about that, ask in class. Take care.